Beautiful outside. We appreciate you being here instead of the golf course. My name is Allison Bamberger. I am the program director here at the Masonry Institute of St. Louis, and I want to welcome you all. So today, we're so excited to have Dr. McGinley here to talk about cost-effective, energy-efficient design and high-performance masonry walls. As you know, this is a seminar for 1 AIA credit, and we will be issuing those within the next week. You'll also be getting a survey in your email to ask you about your experience both with our new tech and with this seminar and Dr. McGinley as well. So we really look forward to any feedback you have, good, bad, ugly, we want to hear it all. So we appreciate that. It really helps us do better each and every time. First, we want to go ahead and introduce our staff. We've got everyone over here. Bruce Augustine. Hello, Bruce. He's our technical director. If you have any engineering questions, he is a fantastic resource and someone that's great to know. Next to him, we have Pam Holloway. She keeps the lights on, keeps everything running. When you call, this is probably who you'll talk to. Next, we've got Greg Bryant. He's the head of the Structural Coalition. So anything masonry structural that you've got questions about, Greg, amazing resource. His office is right out here. Come say hello and see all that he has to offer. It's wonderful. Today, I will pass around a box for our gift card, our business card giveaway. If you want to throw your business card in the box, if I give it to you, just pass it on to the side, and then when you're at the end of the row, pass it up and back. It will just snake across this way. We'll go ahead and pick it at the end, and we've got a copy of the TMS 402-602-22 to give away. So that's pretty exciting. We'll do that at the end. And we also want to thank SpecMix today. They are the sponsor of our event. We really appreciate all that they do to sponsor the Masonry Institute of St. Louis, and then all the help that they give Masons in the area. So thank you very much, SpecMix. So next month, December 4th, we've got Phil Ledent coming in from the Masonry Institute of Michigan. That would be a fantastic seminar. The registration email went out this morning. If you didn't receive it, let me know. I'll either resend or we can just get you registered. My office is right there. Stop by afterwards. We would love to see you for that one. Again, another AIA credit opportunity. And it's going to be a really wonderful presentation. I just started looking at it this morning, and I think he's got a lot of great things to say. So we look forward to that. But today, of course, without further ado, we have Dr. McGinley from the University of Louisville. We so appreciate you driving up here and joining us again. He is truly an alum, given many great seminars here before. So without further ado, Dr. McGinley, thank you.
Thank you. Can you hear me? Okay. All right. Good to hear. All right. Supposedly I'm being recorded, so I'll have to keep the really bad joke down. All right. And notice we're filling up from the back. All right. Towards the front. There's plenty of space here if you want to come up front. I do not bite. We're good. I do appreciate the opportunity here for the opportunity to come up and talk to you a little bit today, and with my good friends at the Masonry Institute here, appreciate this opportunity. What are we going to talk about today? We're going to talk about energy. Energy performance in masonry walls in particular. So what we're going to do here today is hopefully give you a better understanding of how buildings perform with respect to energy and how masonry walls, particularly the exterior walls, will impact that energy performance, and then hopefully give you guidance on how to design it. All right. Just a little question I have for you. It's not a quiz, etc. Those of you who design masonry walls, exterior masonry walls, how many people use the R value tables in the IEC? Just to show a hand. How many people use the U value table? Two people, okay. How many people have ever done a holistic building energy design? That's what I thought. Okay. I'm going to hopefully give you a little backdoor into how to do those a little later on. The DOE is putting the dollars developing some tools that may make that easier. All right. We'll go in here and look at energy related. The vast majority of these exterior wall designs are done using these whole building energy analysis path, however, has been in the code, I think at least 30 years. And that path is the only path that will adequately address or accurately address the impact of mass walls on that building's energy performance. Prescriptive path does account for it a little bit, but it's very inaccurate, very conservative. But we'll talk about that as we go through today. We'll look at a number of holistic building energy analysis investigations in the published literature out there, look at what things really impact the performance in the building, and then hopefully give you some guidance on how to do your designs better later on. All right, here's the basic Bible that we operate on, right? 2000 IECC 2000, we've got 15 up here. Is that the one that's in effect in Missouri? All right, you have that weird thing that jurisdictions, different jurisdictions accept different levels. The latest one is 2021. They're working on a new one soon in here. What you look at since 2000 and about even 1999, 2000, they've been incrementing all of the prescriptive requirements in the code, ratcheting them up, and they have, if you go on the DOE website, there is a really neat graph where they've shown how these subsequent prescriptive requirements in the code have reduced by 50% the energy use in new building construction, right? That's what they project all of these requirements are. And so if you look at the step down, each code prescriptive requirements have been designed to reduce the amount of energy used in new construction. One of the things in here that they have is they have the ASHRAE 90.1. That's the code I generally use because the IECC is based off of the ASHRAE code. All right, very consistent with it. This one's created by MEP engineers, and it's a little easier for me to follow. And there's a little bit more flexibility in it, although the prescriptive requirements are essentially the same. This is that standard, the 90.1. I've got this one that's 2013. There's a new edition out. I had that slide, so I apologize for that. And this is the one I look at. Now, when we design our building systems, we have 8 different climate zones in the United States. What we designed down in that little place down in Florida differs from what we designed in Duluth, Minnesota. All right, we have different requirements for each one of those, as you might expect. This is predominantly a cooling climate, 2 and 1. This is predominantly a heating climate, climate zone 7, and then we have a climate zone 8 up in Alaska. All right, now looking at the prescriptive requirements in each of the zones, we have these tables. This, by the way, is the ASHRAE table. I like that better because in the IECC, they separate out the R value tables from the U value tables. In the ASHRAE standard, they put both in the one table. They separate it with climate zones. All right, and I like that better. If you look at walls above grade, mass walls, for which masonry walls imply, so they're a mass wall, they have a continuous insulation requirement for climate zone 4B, and I think that's in 4B area, okay, in this state. You have a continuous insulation requirement of 9.5. I don't know of any insulation that's exactly 9.5. The 2 inches of extruded polystyrene will give you a 10, and that's typically what you use, right? And then they got that lovely little CI there that has caused all sorts of wonderful problems. all right? And if you get nothing out of this particular thing to ignore this and go to that, I've done my job, all right? I'm going to promote the heck out of that. If you're going to do prescriptive design, at least use the U values. There's a reason for that. That's because you don't have to have continuous installation. End of story. All right? That's the big plus to that. And how do I get these R value compliance? I personally like cavity walls. Nice thing about a cavity wall, putting the insulation in here, is it's protected from fire on both sides by masonry. Okay? Don't have to put anything more in there. Protects that both from fire and for degradation in here. It's a great way to go about it. It's also the R values on that wall, or U values, are independent of the growth that's put in that wall. So you can use it solidly grouted or partially grouted walls work quite well. We can put insulation on the interior, fur it out, do that a lot. Put the insulation on the inside, and then I have fur strips in there. I can also put externally applied insulation systems, whether it's EIFS or true stucco with insulation on it, works very well. Okay? Great way to prescriptively meet the energy code. All right. Now, this, by the way, is a typical table that you will see in the IECC, and it's broken down into climate zone. This is the prescriptive R value tables. And you will note that there are conditions and climate zones where you do not need insulation exterior to that wall, either on the interior or on the exterior. If you have a partially grouted wall, that means vertical reinforcing no more often than 32 inches on the center, and horizontal reinforcement no more than every 4 feet. And then the cores are filled with foam that meets the 0.44 BTUs, etc. And by the way, there's lots of them out there. Loose fill will meet that requirement, as will most of the foams that are used. Then I need no external installation. All right. Now, good news is we were operating in the blind for quite a number of years. Now there's 2 brand new codes out here for mass wall, both concrete and masonry. We have a new commercial standard out there, the ACI TMS code 122.3. That's for commercial buildings. The 122.2 is for residential buildings. And it gives you a lot of really good guidance on how to meet the prescriptive requirements in the energy code as you're going through doing those prescriptive designs. In particular, it addresses the U values, and we'll get into that in a little bit more detail in the subsequent slides. Does the same thing for residential. There's another code out there that addresses this whole issue of thermal bridging, and it will give you guidance on when you have to worry about it. Okay. Anyway, reminds me of a very bad Cheech Chong video. Anyway, all right. Dave's not here, if you remember that. There's enough gray hair in here, I'm sure you remember. All right. And those of you who are younger, you Google it. All right. Dave's not here, he'll bring it up. Hilarious. Or at least I thought so. Anyway, in these requirements, we have these trade-off requirements, so that goes through the U values and the R values, and they're consistent with prescriptive requirements code. But they also give you guidance on different assemblies for the U values, what those values are, so it makes it just as easy and better for using the U value compliance method. They give you all of the cookie cutter methodology to get in there and meet those criteria. So these are very, very good in going through that. They also give you the methodology you need for accounting for the impact of these masonry walls when you do holistic buildings. They also give you guidance on how to do the com check correctly. If you're using trade-off, how many people have used com check? Hands up. Okay. You have more people who use com check for compliance, yet very few hands went up when you said you never designed there. So I'm a little surprised by that, but that's good. At least we're talking to the right people. All right, so what you have in here is a bunch of U value compliance. So use the U value table. I'll say that one more time. Use the U value tables, not the R tables, because the continuous installation requirements are not there. There's a reason why that's important. Cost of the walls go down. That's almost a guarantee. So there are requirements. If you take that entire wall there, you can account for every piece that's in that wall to resist that thermal movement through that skin. All right? That's what it's basically telling you. So if you have foam in here, you can account for that. If you're just putting the insulation with a gap in there, that will actually reduce the amount of thermal movement. If you put insulation in there, you can get away with less insulation than you would with the continuous requirement. There's lots of guides out there. There's information on, and I'm sorry, the hardscape, the concrete masonry group now, they renamed themselves. I still call it the National Concrete Masonry Association, NCMA. It'll still get you there. It's still there. They still maintain that website. But they have a guide in here, particularly the Concrete Masonry Assembly Guide. You don't need to get that, but it gives you a lot more values than the other guides I'll show you in a second. All right. In the codes that I put up there, the 122.2 and the 122.3, commercial versus residential, they have all these tables that give you the U values for different configurations, different size blocks, different densities, all of that are listed right there. So you pick the number up. If it meets the criteria for the assembly that you're done, that's it. That's all you need to do. Those U value compliant. All right? You can account for the impact of the veneer. And it does have a positive impact if you're going with the cavity wall. So you can account for that. If you use some of these unique elements in here where you're foaming it, or if you're putting they've got a new system in there where you put inserts in there. And they've actually found through testing that those inserts do not negatively impact the flexural component, but greatly enhance the thermal resistance of that wall, i.e. reduce the U value. And there are provisions in this consensus standard. Okay, it's a standard gone through review, okay, all the way through it, and it's an accepted standard. We're pushing really hard to get it in the IBC, but we've had good, it's just been out the last, I guess, 6 months now, and we've had people using it with code officials already. Right. Now, if you're close on a wall with the U value tables, you can use com check. Let's say your wall is just not quite there. Okay, you don't get it below the value you need for that, the climate zone. Well, you can go through and use com check. It's an easy way to trade it off, but that separates the energy budget between 3 different areas, excuse me, in your building. And you can't trade off between those different elements. To do that trade-off, you need to do a holistic building analysis. That's why if I take 2 inches of insulation and add that to the roof, I can't back off 2 inches of insulation on the walls. It doesn't work that way. ComTech is based off a holistic building design, and they've created the equations that are in background there as a approximation of a holistic building design. And bluntly, the envelope, after a little bit of insulation, does not impact the behavior of the building. And that's why you don't get much of a trade-off with that. But it does, if you're close, it works out pretty good. Note, and I'll say this again, you can only trade off the envelope element. So you're going to go through there, you're going to go look at envelope in here with the ComCheck. This is the free version I downloaded a while back. This one complies all the way up to the 2015 EICC, the Energy Code. I haven't downloaded the latest. I understand it's up to the 221 now, but I haven't got that, so I've got the slide in here. And it's a pretty simple software. And you can run it either on your own machine, or you can download it and run it. Download it, run it on your own machine, or actually do it on the web. As I said, it's easy trade-off. You can use it pretty well everywhere in the United States except for Washington, California. California does its own thing in many of the codes. Surprisingly, so does Washington. Missouri is that nice green one where it varies with jurisdiction. But you can use it in most cases. And basically, it gives you this basic element in here. You input your building, some basic information out of it, where it's located, etc. I don't ever put in any of the other stuff in here. They say I can't trade off that anyway on the envelope. So I'm just putting it in there. One thing I want to highlight in here is when you go down there and you have mass wall and there's a drop down, be real careful in here. Do not use concrete block in here. That number is out of the ASHRAE manual, and it's really old and it's really inaccurate. All right? So what you can do is go down to mass wall, and then you can pull in the U value directly and the specific gravity, as well as the value in here, the heat capacity value. These you can get from the tech notes. You can get it from the 122 elements. The heat capacity, the U factors, they're all in there. There's a variety of different locations where they are. Use those. It will have not an insignificant impact on whether or not you meet ComTech criteria. All right? So you can go through there, and you can, if you go through that, if I use the prescriptive R value, I'd need 9.5. If I did the prescriptive U value with trade-offs back and forth, I can play around and get lower values for the R values. Note, those aren't continuous insulation. Those are the total insulation effective on that wall. It's just 1 over the U value. And so I can use every layer in that wall to meet them, instead of requiring at least 9.5 CI continuous insulation on it. Significantly reduces the cost of that wall, gives you exactly the same performance. No difference. And I'll prove that to you later on in some of the studies that we have. Putting insulation. By the way, anyone here from Texas? Oh, good. All right. In Texas, I've given this talk in Texas, by the way, and I'll say the same thing to them. So I'm maybe a little silly, but I'll do it anyway. A little bit is good. A lot is a lot better, right? That's, by the way, a religion test. All right. That's not true for art. I'll show you that in a little bit. All right. So con check and the story in here. Large increases in R anywhere along in there are not going to get you large decreases in our other places. That's just not the way that works. Okay? And I'll show that in following slides. We'll look at what the performance of the building is like with huge ranges in R value. Now, the other thing that I've been called more often than I'd like about, oh, we got this particular tie system is used. We got a lot of thermal bridging. I got a shelf angle in here. They're not allowing it. I got to stand that shelf angle up and put continuous insulation. Now they're disallowing the brackets. Has to be continuous insulation. Well, how do I attach my shelf angle to insulation? Not possible. Okay, and a lot of that is based off a study. And actually, I went to graduate school by the guy who wrote this. And he and I have had some discussions on that later, since then. But anyway, this particular shelf angle is big hunk of metal that goes through there. We have all these ties in there, and they've got these steady state analyses that show that you can get a significant increase in the amount of energy that's going through that wall. And it's true in a steady state, but as you saw today, the temperature outside is not steady. And that actually helps when you have large, heavy walls in there. One thing it does show you, it's a justification I like to pull up in here, is stainless steel has a much lower thermal conductivity than regular carbon steel. And so you'll actually reduce thermal bridging. And the fact that we put not stainless steel ties in there for a very small savings in the wall, and we drastically reduce the potential lifespan of that system, I've never understood that. Almost every other developed country in the world requires stainless steel in those applications, in most climate zones. Not all. They've done studies in here with these shelf angles to say, oh my goodness, we can have up to 40% reduction in that effective thermal resistance of that wall. Steady state, remember. Okay, and so there have been a number of companies that have developed standoff bracket systems, the fast system line by parallel ties, that allow you to pull up and put the continuous flashing down there. You still got a big chunk of metal bridging the insulation. But the big issue in here is I've got a big mass wall in here. And I've got big heavy-duty walls in there. They're acting as a capacitor. When you're looking at impedance of thermal movements, you have resistance, and then you have essentially like a capacitor in an electric system. The mass acts as that, and it resists motion when you have a dynamic push. Dynamic push means I have a steady state temperature on the inside, but the outside is moving in and out. All right. And that has a significant impact. So, we developed another standard. It's been up since 2021. And this is this whole idea of thermal bridging. How do you account for that in mass walls? First thing is, up to a climate zone 4, ignore it. Don't need to address it. It has almost no impact on the behavior of the wall. All right? So you now have code provisions that say, don't worry about it, restrictively. So we're good. And even in climate zones 5 5 through 8, they give you guidance. They go through here and it says, okay, if I have certain square inches, right? A certain amount of area of different types of steel penetrating that thermal resistance barrier, the insulation, then I'm okay. Most ties would fall in under these conditions. Most shelf angles fall into that category. Even when we're going into climate zone 5, okay? Not all, but most. So, they give you guidance. They give you something to hang your hat on in a code compliant manner, okay, prescriptive. They also go into here and they show you how to get the effective U value for different configurations accounting for this thermal bridging. So that if you do a holistic building analysis, or you're going in and using com check, you have a guidance in here that leads you through that relatively straightforward element or calculation. They also talk about what to do if you've got balconies, right? You're continuing that concrete balcony out from the floor slab, right? What do you do in those cases? They give you guidance on how to do that prescriptively in there. Okay? Air does not carry much structural load, trust me. All right. Going through in here, the shelf angles supporting masonry veneer, they go through a lot of basic description and how to address these thermal bridging concerns. They also give you guidance in there on how to go through and deal with some of these configurations, parapet walls, that sort of thing. There's all sorts of basic detailing that are covered within that thermal bridging. So I would highly recommend it. Get it. You can get it in PDF version if you want. It's available on the ECI website. Right? Well worth it. Okay. Now, the best way, however, to go through and address these conditions is doing holistic building design. The software that I use is generally Energy Plus. I've used GoTo, I've used a variety of others to do these analysis over the years. This is a code compliance method. The third way you can go about show code compliance, if you have more than 30% fenestrations in your building, you must do this. You can't comply because the limitations on fenestrations in your building would kick you out of that, okay, out of that prescriptive requirement. Many schools, I had to point that out to architects on that, because the big thing is to, you got to have all this outdoor light, right? With fenestrations, people want outdoor lights in the classroom environment. Outdoor light has a lot of benefit. Problem is you can't do it prescriptively. So you got to go this route. There's also Appendix G in ASHRAE 90.1, similar allowance. In that particular method that says, okay, I design my building prescriptively to meet the prescriptive requirements. I analyze it. I get an annual energy cost. That proposed design must have an equal or lower cost when I reanalyze it in the proposed configuration. That's basically the way that works. What's interesting is you used to be able to go in and with the low cost of gas, go in and put more gas heaters, etc. in there. You could drive that cost down. Now they're changing that loophole as a way to play that game. It's been becoming less and less. In fact, I was at a state code meeting where they disallowed gas furnaces in residential applications in Washington State. You cannot use stovetop gas anymore. By the way, the Gas Producers Association of the U.S. is taking that to court. And you wonder why. I didn't. All right. However, when you go into these kind of analysis, they more accurately predict the impact of these mass walls. Anybody done any passive solar, passive house design? Okay, thermal mass is your friend, right? That's where you store the energy, the thermal energy in the building. Well, if your wall is big, massive concrete walls, concrete masonry walls, or brick and block masonry walls, how do you use that adequately in the design if you thermally isolate it? You can't. So you need to adjust that. We'll talk a little bit about that a little bit later on in some of these studies. So to account for that thermal mass effect, you need to do a holistic design. All right, so we did a study a number of years ago. We were building a lot of schools. We had a number of new schools being designed in Kentucky. Problem is the cost per square foot were going out the door. I mean, they were really, really high. And the big push there was to get zero net schools, okay? So they were doing ICF and a bunch of other stuff to it, a lot of PV. And so I was hired by the state to go and do a cost study that was basically, if I have $1 to spend, where am I going to get the best return for energy in the building? So we did a series of studies. We used a typical building here, and it was a prototype building that was at the time promoted as being a standard middle school. About 160,000 square foot, two-story prototype. It had an auditorium, it had a gymnasium, it had a cafeteria. So it's a good basic building. It's quite modern. Actually, it built one just very similar, like Wake County, North Carolina. We looked at in here, we had cavity walls in here, typical. They were prescriptively designed using energy standards at the time. T12s were what was required, high beam halides for the school gym areas. We used the typical R values on the walls, effective R26. Interesting note, at that time, we did not have the continuous insulation requirement. And we ran a series of analyses. This is a model, schematic model, comes out in SketchUp, by the way. And this is the way that basic system worked. And so we looked at a variety of things. We looked at varying the insulation. From prescriptive requirements, we increased the insulation 100%. We got less than 0.7% change in energy. This is climate zone 4, same 1 year. Did the same thing for the walls. Okay, note 189-year payback. Did the same thing when we were looking at prescriptive requirements in the walls. And some of those things, going up a little bit in the insulation had almost no impact, but it cost us almost nothing to do it. The payback was pretty good. However, going to ICF, what amazed me when I was looked into the detail, I thought, oh, ICF is way cheaper. It was almost 25% more expensive to build the ICF wall than a typical cavity wall. Blew my mind. All right, 335 was the payback. Now, I've been in a 300-year-old school building, but it was in Europe. And not in here. Air barriers, basically meeting the code prescriptive, making it more airtight than help you. Windows, here was interesting, we have U values for windows. So we backed off the U value requirements and we used a different climate zone. Climate zone 1 and 2 has higher U value allowances for those fenestrations. Lower cost and almost no impact going to crappier windows. Interesting. It's all about the amount of fenestrations. You change 10% on the fenestrations, you'll get a significant impact. Playing with the U values do almost nothing for you, right? That's another thing I wanted to bring to your attention. Okay, then we said, okay, what will make a difference? It's all about the HVAC systems and the control. All right, we were able to go for ground source heat pumps, say 71%. Even then, because we didn't do any incentives, etc., because schools aren't eligible for that, or at least at that time, 22 years. Now, that cost has come down because more and more people are using ground source. Boilers, setbacks, etc. We were able to, looking at a combination of those, not ground source, get about 50%, over 50% reduction in there, but paybacks were only 3.5 years. Playing around with the lights, the controls, all of that. Simple, cheap, that's where the sweet spot. If you want to save energy, you want to save money, that's the way to go. It's all about the HVAC. All right. Did the same thing for a variety of different buildings that are built out of masonry. We looked at warehouses. And these are prototype warehouses that were designed by the DOE to be consistent with about 80% of typical warehouse design. We looked at their performance in a variety of climate zones. We did the same thing with supermarkets. They don't have that anymore, and I'll show you why in a minute. And then we recognized that this basic building is essentially a box store. Okay, we took out the refrigeration and the bakery, etc. in that, and we ran that basic 50,000 square foot, about 45,000 square foot element in there. We came up with, how does that perform? We looked at a variety of different configurations. First of all, we looked at the wall insulation values. What we did in here is we changed the insulation value from the code baseline in here, and we played around with increases of wall insulation and roof insulation, and that is the blue here. Not a lot of difference in almost every climate zone in here. As you get up into the predominant heating area, you get more of an impact. But we just made simple changes in efficiency of the HVAC system, the heating system in there, way bigger impact. And these are way more cost effective, right? Costs you a lot less than putting additional insulation over that huge area. Way easier. We also took a look at what is the actual performance of these foam insulated walls, right? Where the cavities are foamed. We looked at a bare wall, no foam. We looked at grout just at 4 foot on center, which is typical. And we did bare, and then we put the insulation in there. And you will note the U value here, bare is about 0.5, with the insulation in there is about 0.287. So we significantly reduced the U value, the thermal transmission. And what we found, see the big hash marks in here? That's the bare wall. And yeah, I need insulation in there. I don't want it bare, because there's a lot of energy going through that wall. But foaming the wall, there's the baseline, the red one. But foaming the wall right in here gives us almost the same performance in almost every climate zone. Not a lot of difference. Okay? We put a little bit more insulation on the roof in there. We were able to bring that down a little bit further. 1 inch more, 2 inch more on the roof. Okay, we were able to bring that down, and not down to the performance in the heating predominant mode or locations, but we had a significant impact on that. All right, did the same thing with the warehouse. Now, what we also did in these ones is we went through, this one was just looking at the impact of the performance. And these values in here are what they call the energy use index. How many kBTUs per square foot for that building, okay? We then looked at the holistic energy analysis method where we looked at energy budget, yearly basis. We did it in the warehouse and we said, okay, the baseline for the different heating zones, we used the typical state average energy cost for that state for climate zone 7, etc. And we worked out the red bars here were the average energy at the baseline. We then put 8-inch CM root with just lower 2 inches, 2 inches of additional insulation on the roof, and used electronic valves on the T12. That's very simple. What we found is we were able to be in code compliance all the way up to the 6B using the holistic method. No external insulation on the wall. Right? We got there when we went into the 12-inch, we got all the way to climate zone 7. No problem at all. Then, when we got up into climate zone 7, 8-inch CMU, lower ballast, then we put occupancy sensors in the warehouse. So we turn the lights off and on. Not a code requirement, and we could use that for code compliance. And we were able to be in compliance, which, by the way, cost us $150. Insignificant. All right. Did the same thing for the other prototypes. Again, that blue value there is an interesting value. That is the supermarket prototype with the refrigerator. All right. The red bar is the supermarket without the refrigerators. Why are we worried about the opaque wall thermal resistance in that building? Because the code won't allow us to account for the more efficient refrigerators because it's not considered fixed equipment. All right? And so it can't be used for code compliance, yet it dominates the behavior. But in every case, we are able to get code compliance using this holistic building analysis quite simply. And when we looked at capital costs, there were lower capital costs, and we saved anywhere from $3,000 to $15,000 a year in energy costs. Okay? Owners will be happy about that. All right. Now, one of the reasons that is occurring is the following. If you look at it, the R value of a bare masonry wall is right about here. By the way, what this vertical axis is the amount of energy that goes through the wall. Okay? And we do that called the energy performance factor. The higher that number, the more energy will go through for a fixed delta G. Now, looking at here, you have an R of about 2.5 for a standard wall. If I push it up and get a little bit more in here, about 50% increase to an R5 in there, I drag that down so I have a significant amount of energy reduction through that wall. But if I go and double that again to an R10, I'm on the flat side of the curve. The code minimums for each area is in this flat part of that curve in every single building. That's why it's happening. Now, I want to talk briefly about thermal mass. Here's a typical ICF configuration. By the way, that's from the architect that was designing the school. I couldn't draw that neatly. So I drew this in AutoCAD. Here's a typical cavity wall, right? This gives me comparable R. But if you look at the impact, I'm isolating that mass away from the internal conditioned environment. I want that mass against the internal environment because that acts as a mitigator. So I get fluctuations in energy. I bring kids in and out of a classroom. I spike that air volume's temperature because people give off heat. All right? They turn things on, it spikes up quickly. That wall in direct contact with that environment will stop that from happening. Okay, and it has a beneficial impact on the HVAC costs and the amount of energy used on that interior. Significant. All right, so we then extended, I had an additional study we did fairly recently where we looked at passive house. And I already found out we have a few people that have done passive designs. Anybody done a passive house? Okay. The thought had been 10 watts per square meter for the exterior wall systems and roof. They had restricted to that level. They actually changed that about 8 years ago in the US, and they found that wasn't effective. The study was done by the DOE, and they published a bunch of information on that, by the way, just so you know. So what we did was look at passive house analysis. We used the standard MISL prototype for houses, which they developed for energy studies. And we looked at typical studded wall systems in there. And we took a look at a number of different climates. We went from Miami, Louisville, which was very similar to this climate, a mixed climate, and then Duluth. And we played around with the R values in this wall from about the code minimum values that would be defined in here all the way along. See how flat that is? So I've got people putting R60 walls in to meet passive house, which if you use the prescriptive R, 10 watts per square meter, that's kind of what you're pushing for. Has no impact in Florida. In fact, actually can increase in certain conditions the cooling loads in that building because your interior load dominated is what they call it. And in Louisville, you have a small effect, right? 33 to 32, 1 in 30, right? Impact. And that's going from an R20 to an R60. Okay, and these are roof and walls, actually R5 to an R6. All right, where do you have the impact? It's all about the HVAC system. That's what increases or decreases the energy. We looked at passive house requirements, and they have a new requirement in here, and I wanted to bring it to your attention. 4.75 kBTUs per square foot is what they're advocating, and of which they have 7.6 MMBTUs for heating and cooling as the maximum. And that's based off of what typical would be available for you to generate using sustainable sources like PV. All right? So we did that, went through there, we were able to get passive house designs for that. Then we went in and we said, okay, I'm going to replace the exterior walls with masonry or other mass walls in there to see what that impact was. We looked at that wall, and then we were going to put insulation either in the interior or the exterior. You could do it that way. And with the mass wall, there's even less impact on the R value of the wall. In every case here, except when you started to go in here. By the way, that's no insulation again. Okay, and this one is, I believe this is for Louisville, yeah. And you can see I need some insulation, but once I got some in here, by the way, that's an R5. Continuous insulation on that. Then we go to an R10, R15, all the way up to an R60 on that wall. 31.9, 33. 1 in 30. Almost double the wall cost. And I get almost no impact. All right, similarly, we did it for Duluth. More of an impact over a longer period of time, but just so you know, that's about the code prescriptive requirement. That's about the code prescriptive requirement there. All right? Then we went in there and did the same thing for the cooling environment. Got about the same value. All right? So the end of the story is exterior masonry walls can be used to meet these passive houses, but you only need about the code level prescriptive requirements to meet that. And you've got to do a holistic building design to get there, but it's really easy to do with the BOP program. It's a real simple cookie cutter analysis. You just have simple choices to make, and it's free. 7 or 8 YouTube videos on how to run that. And I trained my graduate student to do that in about a week. Right? It's not hard to do. Speaking of hard to do in holistic building designs, there is a new DOE software out there called Asset Score. Anybody familiar with Energy Star? You know, that's where you put your bills in there and get Energy Star certified and all that. Well, they took that basic database and then they coupled that with a simple building input design where you can put in some basic parameters in the building. It creates a open studio Energy Plus model, holistic building model for you. And there's a number of basic uses it uses in there. Then it looks at those and what are your typical HVAC units and how are they typically configured? Creates that for you. You can go in and look at different things that might change that element in there. And you can run that, and it's, by the way, a web-based system where you go in and run it, and it comes up with a score of your building. And then it tells you what you can do to improve the behavior of your building and the rough costs associated with it. But what I really like about it is once you've run it, it will allow you to download an open studio model, pull it into the open studio, do a little bit of analysis in here, get this energy budget value there. Takes less than a day. I've had people quote holistic building designs up to $50,000. That's a pretty good wage for one day's work. Right? I wish I could get it. All right? I'm not that good. All right. So, if you got nothing more out of what I gave you today, 3 things. Number 1, use the U value table. Number 2, there are 3 brand new codes out there that will give you code-compliant guidance on how to prescriptively use those U value tables in your design. Finally, it's not that hard to do holistic building design with some of the new tools that the DOT has developed. So, I appreciate your time today, and thank you for listening to me. If you have any questions, I got a few minutes now that I can entertain questions. Has anybody stayed awake?
Is there a factor with paper
There is a air infiltration requirement in holistic. And so you can vary that. We did that in our few studies. But right now, what's the requirement for an air barrier? Thou shalt have one, right? Vapor is a different issue. That has less impact on the energy used. It has a lot more impact on the durability and where is that condensation point in there, and that's, to do a proper analysis on that, you need to run the Woofy program or something equivalent to that. There are prescriptive requirements. My problem is I've seen people unintentionally put a vapor barrier on one side of the wall and end up with a vapor barrier on the other, and they're trapping it in between them, and it's way better to have no vapor barrier. And that's the nice thing about concrete or concrete pastry or masonry walls, they can get wet and dry. So in some cases, particularly in mine, I've done some designs in there, and I said, look, you're gonna heat a little bit more latent heat, but drive to the interior, you have control over that. You can, when you're in cooling mode, dry that air out real fast. And so it's better if you've got that on the interior width of the wall, dry to the interior. Don't try to dry to the exterior, particularly in a environment. Which wall?
Chrome walls.
Oh, yeah, passive thermal wall.
Yes. Because of the glass exterior wall, which has almost no R value.
Yeah.
The thermal wall on the inside, I've run problems trying to get people to set the R value, putting a step back into the wall.
Well, that's the whole problem with that prescriptive design.
Right.
You can, with BIOC, do that. You can incorporate it into that one where you need that. Now, one way to do it is you've got the thermal resistance of that by two areas, because you're looking at solar heat. So if you have two wall insulation there, you'd be surprised at how much impact that will be. Well, that's because you're doing prescriptively. If you do it with the holistic one, in which at this level, you're at a much higher performance requirement than the prescriptively designed one.
All right, folks, thank you so much. We are right up at 1 o'clock. I believe Dr. McGinley will stick around if you've got more questions. But thank you so much. That was incredibly thorough. I think everybody got a lot out of it. The last thing we will ask of you, Dr. McGinley, is to choose a winner for our giveaway today. Do you mind?
No. Let's see, I gotta dig in here.
All right, who we got?
All right, we have Eric Rubin.
BSI? All right, come on up. Thank you folks so much. Please be on the lookout for the survey that we'll be sending tomorrow and your AIA credit certificate that will be coming within the next week. We hope to see you in December.